Hi everybody, welcome back to the Feynman technique. This is kind of a follow-up video to my last one, where I derived the generalized factorial, except without this negative sign in there. So this we're going to find a generalized half factorial for negative of 2n plus 1 over 2 factorial. In other words, and also n has to be a natural number and n is not equal to 0. Although we can easily find the factorial of negative 1/2. In fact, I did it in the last video. And we're going to start there. We're going to start with the fact that negative 1/2 factorial is equal to the square root of pi. I'm not going to show that again. I've showed that in two separate videos. One of them was my last video, and one of them was some other previous video, and I think it literally has the title negative 1/2 factorial. So take a look at those if you want to see how I get that. But also what we want to keep in mind is that n minus 1 factorial is always going to be equal to n factorial divided by n. That's how factorials behave. For instance, if we let n minus 1 equal 5, that would be 4 factorial is equal to 5 factorial divided by 5. So, yeah. So we're gonna use this fact, and we're just gonna start using it right away. And we will set our n minus 1 equal to negative 3/2. So, if our n minus 1 is negative 3/2, we have negative 3/2 factorial is equal to, well, if our n minus 1 is negative 3/2, then our n is negative 1/2. So we would have negative 1/2 factorial over, our n again is negative 1/2. We can replace this negative 1/2 factorial with the square root of pi, because we already know that. We started with that. So, square root of pi. And we can see that this is going to be equal to negative 2 times the square root of pi. All right, let's keep going. Let's set our n minus 1 equal to negative 5/2. So, negative 5/2 factorial will be equal to, well, let's see, if our n minus 1 is negative 5/2, then our n is negative 3/2. So we'd have negative 3/2 factorial over negative 3/2. Okay, well, we know from our previous result that negative 3/2 factorial is negative 2 times the square root of pi. This is negative 2 times the square root of pi. Get rid of the negative signs, multiply the top and the bottom by 2, and we get that this is equal to 4 square root of pi over 3. Let's do a couple more. Let's set our n minus 1 equal to negative 7/2. So negative 7/2 factorial will be equal to, well, if our n minus 1 is negative 7/2, then our n is negative 5/2. So we're going to have negative 5/2 factorial over negative 5/2. We know from our previous result that this is 4 square root of pi over 3. Multiplying the top and the bottom by 2 gives us 8. Now multiplying the top and the hold on a second. Let's undo that. Okay, so this is true. So let's bring the negative sign out front. And then make this a 4 square root of pi over 3 times 2 over 5. Which would make the entire thing equal to 8 square root of pi over 15. I'm sorry, negative 8 square root of pi over 15. One more time. Negative 9 halves factorial. Well, that's our n minus 1. So that's going to be equal to, well, our n would be negative 7 halves factorial over negative 7 halves. Yeah, okay. Well, our negative 7 halves factorial is negative 8 square root of pi over 15 times divided by negative 7 halves, or times negative 2 over 7. That's a 16. And then this would become a 105. And that's enough to find our pattern. Okay. So it looks like negative 2n plus 1 over 2 factorial is going to be alternating. Let's see. We don't want n to be 0, so we have to start at n equals 1. That would correspond to this term right here. So if our n is equal to 1, and this is a negative term, we would have a negative 1 to the n. That will definitely be part of it. Okay. Well, let's write this as negative 2 square root of pi over 1. All right. And it looks like our numerators are all factors of 2. And our first term is, it looks like 2 to the 1, and that corresponds with n equals 1. So it's just 2 to the n over, well, let's see, we have an odd double factorial in the denominator. Let's see, this would just be, it looks like 2n minus 1 double factorial. Because our n equals 1 term would correspond with a 1, which is 1 double factorial. So if our n is equal to 1, 2 times 1 is 1 minus 1 is 1 double factorial. This would be our n equals 2 term, so 2n is 4 minus 1 is 3, double factorial is 3, and yeah, that's the pattern. So this is the solution, and yeah, that's it. Hope you enjoyed that.